With Owen Lamont, experienced software engineer. He's a member of our local Python meetup in Adelaide. And he's also going to talk about Rust in this Python conference, or Rust for Python developers. He's an experienced developer. I've seen some presentations of Python in the meetup, of Owen in the meetup in Adelaide, and it's really wonderful. And I'm pretty sure you're going to enjoy this one. Thank you, Owen.
Cool. Thank you very much. All right. Thank you for attending. Yeah, my name's Owen, and I wanted to talk about some cool 3D visualization packages in the Python ecosystem. So I'll jump right in. So both the title and a lot of the content for this talk, I was inspired by a PyCon US talk in 2017 by Jake Vanderplas. He's a really great developer and kind of developer advocate, and he's produced a lot of fantastic materials in the kind of Python, data science, and data visualization kind of topics. And in Jake's talk, he put up this map of all these visualization packages in the Python ecosystem. And to very, very quickly recap, when he did his talk, he kind of went around in a circle. He talked to matplotlib and all the satellite packages around that. And then he talked to JavaScript and some of the really popular JavaScript Python integration packages like your Bokeh and Plotly. And then he came back and he talked about D3.js, which is a really popular data visualization package in the JavaScript ecosystem, before finally bringing it around to Altair, which is a visualization package that he's worked on. It's based on the grammar of graphics, and it's very cool. But even though Jake put several 3D visualization packages on his map, he didn't really spend much time speaking to them, which was fair enough. He was covering so much ground, but that sort of bottom left corner around the OpenGL, as well as some of the JavaScript libraries for doing 3D visualizations from Python, didn't get covered very much. So this is what I'm kind of calling the neglected corner of Jake's map, and this is kind of the corner of the ecosystem that I really want to drill into in this presentation. I should mention that this is a slightly polished up version of Jake's original map that now lives on the PyVis site. PyVis, if you're not familiar with it, is a website that tracks like the kind of usage and popularity of lots of the Python visualization packages. I definitely recommend checking it out if you haven't seen it before. All right, so I'm going to talk tech stacks and packages really soon, but before we do that, I want to think about why we might want to use 3D visualizations in Python and why we might not want to use them. What are the potential issues? So what are some reasons for using visualizations? Well, one that's kind of obvious, not necessarily so great, is just because they look cool and they're engaging and fun to watch. And I'm not saying that's a bad reason. I love it when people think my visualizations look cool and want to share them. And engaging is obviously nice. I want to hold on to people's attention and for them to be interested to look at our visualization. But I think we can have issues if that becomes the primary reason for wanting to use 3D, and it can cause some problems. So the reason for this is when we're working in data visualization, we normally want to convey a kind of a clear message. We want to give insights. We want very kind of tell a story with the data, and hopefully that story isn't ambiguous and it's very clear. And 3D rendering has certain properties. And if you use 3D rendering naively, sometimes the properties of the 3D rendering can actually work against the purposes of telling a clear message. So I want to go over that a little bit first. So how can having depth and time in the case of animations make visuals worse? And there's a few reasons for this. So one of the first ones is, normally when we're doing a 3D rendering, we want to simulate both light and shadow or shading, because 3D objects don't look very 3D if they're flat shaded. We want the side facing the virtual light source to be more lit up, the side facing away from the virtual light source to be shaded and darker. But think about the process of shading it, that we're actually fading some of the color and texture on that object to black. So we're deliberately discarding some of the color and texture information on these objects as part of implementing a lighting model, which is a bit funny to think about, that you're deliberately throwing away some of the visual kind of definition and clarity on your objects, but you have to if you want to make them look 3D. Other issues are that perspective can distort your visualization and make some details unclear. So I guess a classic example, if you've ever seen like a 3D pie chart, and whichever slice of the pie chart is closer to the virtual camera by virtue of perspective looks bigger than what it is actually compared to the other slices on the pie. And likewise, if our 3D scenes get very large, then obviously the things that go further off into the distance, we're losing both kind of shape and color and texture precision on them. They're basically getting too small to see clearly. They're getting fewer and fewer pixels that they can render with as they disappear into the distance. So that's a potential problem. A third one is the problem of occlusion. And occlusion is just a fancy word for saying some object in the foreground is blocking our view of some object in the background, so we can't see that background object. And this kind of 3D bar plot, I guess, is a pretty good example of that, where we have tall foreground bars and they're blocking our view of the background bars. We can't see what they are. I guess I'll also quickly note that occlusion isn't always a problem just of what we classify as 3D visualizations. You even have kind of occlusion and overdraw problems in 2D visualizations. If you've ever done a scatter plot in matplotlib, and whichever dots, especially if you use different colored dots, the ones that draw later overdraw the earlier ones. And you can sometimes tweak around with the Z depth of items that you draw in matplotlib, but you can even get that sort of occlusion and foreground objects obscuring background objects happening even there. And I guess lastly, it's quite typical to want to animate when you're doing 3D visualizations. If you have a 3D object, typically you, at the very least, want to be able to animate a camera to move around and see it from multiple sides. That's kind of part of the value of having 3D. But animation brings its own problems. So animation can become distracting if you think like excessive animated GIFs, blink, and kind of tags from 1990s web pages, that sort of style. So it can be distracting. Also, probably worse, if you animate too much motion, especially on a big screen that takes up a big part of people's field of view, you can actually physically make people feel uncomfortable. So I guess an example of this is I used to work at a company that did simulations of these large mine site vehicles, and as part of their testing or just playing around, sometimes we'd throw these vehicles around and they'd be somersaulting through the air. And we're watching this on big screens that take up most of your field of view from the front, and seeing like horizons and really aggressive motion and movement in front of you makes a lot of people very, very uncomfortable when the motion in your kind of visual field is not consistent with your own sense of balance and momentum. So problems like simulator sickness or VR sickness are very real types of motion sickness, and lots of people experience them, and that can be an issue depending on how you do 3D animations. So now I've talked to a lot of reasons why it can be problematic. I want to look at some of the reasons where these features of 3D rendering actually work for us instead of against us. So the first example, the one I'm showing in the top left, is something from a package called Ladybug, and Ladybug analyzes like the solar environments around buildings. So in this case, this is an example of both lighting and shadow where it's not detracting from the message, it is the message that we're trying to convey, and that's kind of an appropriate use. Also, there are times and cases where having animations and interaction over time, it does make sense. So quite often, like for simple plots, we'll just put time on the x-axis. But I guess if we have reason to render stuff in 3D, we're already using up all our spatial axes. We can't map time across one of them. So it makes sense. And for some events, like peak electricity usage or peak traffic convention, we want to see the lead up to an event, the actual event, and kind of the aftermath or after effects of that event. It's also talking about perspective, that sometimes perspective and the sense of scale of objects does actually work for us. So I had one example. It's not specifically related to data visualization, but it is related to 3D rendering. I mentioned that working at this same company that I mentioned before that did mine site vehicle simulations, they used to simulate these really giant vehicles. So these huge haul trucks, huge excavators. These vehicles weigh hundreds of tons, and they're like driving a 4-story building around. They're truly massive. But when trainers and when people try to work on these giant simulated vehicles on the simulator with screens that are just 1 to 2 meters away from your head, you often lost a lot of that sense of scale because your eyes, like your head motion as you moved around and you looked at the screens, your view and your sense of scale was very tied to the physical screens, which were only a few meters away. So even though we're simulating a giant vehicle, it only felt a few meters wide. There might have been other visual cues in the simulation, like trees down below you and small light vehicles, but you still didn't get that sense of scale. And I know one day when, this was early on when the kind of the Oculus and other VR headsets were becoming popular, we tried testing out on users, and suddenly that sense of scale instantly came back. You know, if I'm in a giant excavator, I have to bend back and look up high to see the bucket when it's raised up. I had to physically lean forward and look down to see down where I'm digging. And when I move my head side to side with the VR headset on, my view out the front of the vehicle didn't change very much. So unlike the physical screens, where the VR headset actually helped with that, because the size of my virtual head relative to this virtual giant machine was very, very small, and moving around didn't change my field of view very much. So that sense of scale and perspective really worked in that situation. I guess I'll also mention that sometimes we're visualizing things that are inherently 3D in themselves. So the example on the bottom left, where we're looking at the three-dimensional structure of a protein. And three-dimensional structure is pretty important in this domain because it affects how proteins interact and bind with each other. So I think this is a good use case of using 3D rendering. And lastly, something close to where I work now, I work at a company that does flood mapping. And this is an example where occlusion can work for us, because when we're looking at flood and water raising up and submerging roads and buildings and other valuable infrastructure, that water is now occlusing the stuff behind it. You can no longer see it. So the occlusion actually works for us in that case because it shows us the impact of a flood, what's damaged, what's submerged, what's inundated. Anyway, so hopefully that gives a bit of an idea about when we might want to use 3D rendering and when we might not want to use it. So now I'll get on to the tech stack and packages and so on. So I've done my own kind of mini map of part of the 3D visualization ecosystem in Python. Down the bottom in red, I've drawn the actual, this is supposed to represent the actual physical graphics processor unit hardware, so your NVIDIA cards or your AMD cards or Intel cards and like. And I'm not going to go real that close to the metal in this presentation. I guess one layer up from that in the yellow, we have a lot of the platform APIs, so DirectX for Windows, Metal for Apple and iOS, Vulkan from the Kronos group, and some of the older WebGL and OpenGL ones. So these are the ones that, some of the APIs that abstract away some of the differences between the actual graphics card hardware. And it's getting still lower level than what we'd actually touch in Python, but we're starting to get closer. In the blue level, I'm showing some game engines and some higher level graphics APIs. Some of these do have Python bindings, which I'll speak to in a bit. And at the very top level in the green, I have a selection of Python 3D visualization packages, which I will speak to later on. And I should mention, especially at that blue level and the green level, I'm only showing a very small subset of what's actually out there, just a few kind of representative examples. In reality, both that blue and green layer are much, much wider than what I could ever fit on one slide. So yeah, I'm going to start walking up this tech stack and speak into it a bit. I guess I'll start with OpenGL. This is a little bit of a lie, because there was stuff before. There was 3D rendering before OpenGL, but OpenGL is it's quite old and it's still around, still popular, still used. So I'll talk to that for a little bit. So OpenGL was started by a company called Silicon Graphics back in the 1990s. It was something I looked at doing my undergrad at university, so that was in C and OpenGL and doing really basic 3D rendering. And OpenGL has this concept, as do many other graphics APIs, of a pipeline. So you come up with your three-dimensional vector geometries, you can add light sources and light material properties to these objects, as well as a viewing perspective or a virtual camera, and you put them in the front of the pipeline, and there's a sequence of steps that it goes through, manipulating these geometries before ultimately rasterizing them and turning them into the rendered image from the viewpoint of the camera. And those steps. You can look them up if you're interested. It's changed over time. The earlier versions of OpenGL had very rigid steps that you could tweak the parameters on a bit. You might be able to choose the resolution of the ultimate raster image. You might be able to tweak the field of view angle that this virtual camera had, but you couldn't change much in the pipeline. And over time, these pipelines became more customizable and configurable. You had the advent of shaders, which are C or assembly-like languages that would let you customize different stages of these pipelines. So you would have like vertex and geometry shaders for tweaking how these objects are transformed and warped relative to the viewpoint of the camera. And you'd have things like fragment shaders, which would let you customize the way these things got text rasterized in the end and the ultimate pixel colors that you would see. OpenGL is now managed by a group called the Kronos organization. It's been feature frozen for at least 5 or 6 years. I guess the main reason is that it hasn't really kept up with modern GPU hardware and architectures. So this Kronos organization would prefer you to go into a new lower level graphics API called Vulkan, which I'll speak to in a little bit. All that said, though, OpenGL is still very heavily used, and it underlines a lot of the 3D visualization packages that we have access to in Python. So we are in this bit of this transitionary period where we're still using OpenGL a lot, but all the new work and all the new advancements are happening in different platform APIs. So still kind of riffing on the OpenGL theme a little bit. Later on in the kind of lifecycle of OpenGL, there was OpenGL embedded systems, or OpenGL ES. This was a subset of OpenGL to add support for like mobile devices, so tablets and phones. To my understanding, this is still used on your Android devices today. I believe iOS devices used to use this before they more recently switched over to their Metal API. And a version of OpenGL embedded systems, or OpenGL ES2, later became kind of adapted and rebranded as WebGL. So now it was going to give you hardware-accelerated 3D rendering support for browsers. And WebGL is what underlies a lot of the browser-based data visualization packages that we use in Python today. And lastly, just kind of wrapping up some of the native platform-specific APIs. I spoke to them briefly. So Metal is the new API for newer Apple devices and iOS devices. Vulkan is supposed to be the successor to OpenGL, but it's a much more lower level graphics API than what OpenGL is. And DirectX, which has been around on Windows for a very long time and is up to DirectX 12 at present. I'll say that a lot of game engines do tend to stay up to date with these platform APIs. They care about squeezing as much performance as they can out of the GPUs, but not so many visualization packages have kept up to date with these platform APIs. There's one library that I know of specifically. It's actually a C++ library, dir.im GUI, and there are Python bindings to this library. So as the name implies, it's for creating GUIs or window systems, buttons and icons and elements and widgets. But it also has a subset of its API for doing kind of conventional plotting, like your scatter plots, line plots, and that. And it has bindings that hook into all these platform-specific APIs. So it's very, very performant. So if you ever say need to do a scatter plot with 1 million data points and animate and update that really fast, many, many times a second, that's potentially an interesting one to look at. So the name of one of the most popular Python bindings for that is called dir.pygui. But I didn't include that on the map because as far as I know, it doesn't have any support for 3D rendering. I guess one of the most high-level libraries that I'll talk about related to 3D rendering is this Visualisation Toolkit. It was a C++ library. It was a higher-level abstraction over OpenGL. It has a number of Python binding packages that let you hook in and use it from Python. So there's PyVista, Mayavi, Vito, and more. And I will just quickly mention that PyVista is a personal favorite of mine. I'll speak to it a little bit more later on, but if you're ever interested in getting into 3D rendering using Python, that would be one of my recommendations to try first, just because it has an excellent set of documentation and examples, as well as it supports many, many use cases, from doing real-time rendering to doing offline rendering to images and videos, as well as it works as a standalone script or inside a Jupyter notebook. So it's really versatile and the documentation is great. So it's a personal favorite of mine. A couple more visualization packages that are quite closely tied and coupled to OpenGL are VisPy and GlumpY. I mentioned they're quite low level. These two packages, I believe they're quite interrelated. They've shared some of the same developers. They have some of the same examples, and that GlumpY itself seems to have gone a bit stale. I haven't seen much activity in its repo for the last couple of years. VisPy, on the other hand, is very actively maintained and developed, and I know VisPy is used by certain people in the Earth observation communities, so it's the one that I've used a little bit before as well. And I know with VisPy 2, they're talking about adding Vulkan support and maybe some of those other platform-specific APIs, so that one looks quite interesting to me. In terms of for quite a long time, there have been game engines out for decades, and these game engines quite often have support, like Python bindings that let you hook into them and use them for rendering. So obviously, this is not your traditional data visualization, but if you do need to render three-dimensional scenes in a world that people can interact with, preferably real time, that these offer potentially interesting opportunities. So one very relatively famous open source game engine is the Ogre game engine. I'm not sure if I'll get the acronym quite right, but it's something like Object-Oriented Graphics Rendering Engine. It had Python bindings as a plugin, and I believe its engine natively supports Python now, so you can check out packages for that if you're interested. And another one that I think has huge potential and is really interesting is the Unreal Engine. And I don't know if you've ever checked out like images or videos from Unreal Engine 5 now. I think they're up to version 5.2, but it's an amazing games engine that can do photorealistic graphics and has all sorts of really cool tooling and lighting effects and support. It's so powerful, people can even use it for rendering like movie quality animations, and they do. You cannot use Python in real time when the engine itself is running and people are interacting with it, but it's scene editor that lets you compose the three-dimensional scenes, and the camera and the elements within those scenes has had a Python API for a long time. I've seen some kind of funny old demos of people doing like rendering matplot libplots and having them ultimately added as textures onto 3D models in Unreal. But I think it has so much more potential than that, and I'd be really interested to see more happen in that space. Another potential way of doing 3D rendering in Python is looking at Blender. So Blender is probably the best known open source 3D ray tracer. Ray tracers, if you're not familiar with them, this is for offline rendering. They typically have much more sophisticated lighting models than what your real-time renderers do. And as the name kind of implies, ray tracers model light rays that can both reflect off and refract through multiple 3D geometries in your scene, so you can get these really realistic looking lighting effects and lens effects and so on, and water properties. And Blender has had a Python API for a very long time that lets you automate its rendering as well as build plugins and extensions with it. So that's another one that's potentially interesting if you want to do just offline rendering to still images or to videos via Python. And I guess there's a whole ecosystem of 3D rendering options if you're working in Jupyter, as well as this also includes some web front-end stuff that has Jupyter integrations. And a lot of these packages that I'll mention here are built on WebGL. So I've already spoken to PyVista. That's the image shown in the top left. It's had a Jupyter extension for a while. There's IPyVolume, which lets you do a bunch of interesting 3D rendering in Jupyter. One thing that's particularly cool about this IPyVolume package is it's one of the few packages that lets you programmatically from the Python side save the offline videos or screenshots of your renders. So most of these browser-based data visualization packages, they may have buttons on the JavaScript side to let you save a screenshot of what you're currently seeing. But traditionally, that's been quite complicated to do from the Python side because it's hard for your Python script to know what state the browser is in, whether it's finished rendering one of the frames of your animation or not. But IPyVolume does a bunch of clever tricks to make that work. So I have used it before, and you can use it to save still images, to save animated GIFs, to save MP4 video files. So it's very cool for that, I think. And it's a fairly straightforward API. There's also K3D Jupyter, which is built on WebGL. I think it might have bindings to that VTK as well. I'm not so familiar with that, but they do have a bunch of very cool demos. There's Py3JS. So for those who are not familiar, 3JS is a higher level graphics API in JavaScript built over WebGL, kind of more intended for games development and real-time simulations and that, and it has abstractions for dealing with camera motions and animations and rigging characters and that. So not traditional data visualization, but if you want to do something that's more of an interactive 3D world in a browser, then that might be of potential interest to you. And yeah, Py3JS is just a very kind of low-level Python. It maps very directly to the 3JS functions anyway. And just a couple more quickly, we have PyDeck, which is the Python bindings for the DeckGL JavaScript library, if you haven't seen this before. So this does some very cool geospatial animations and effects. It works with vector tiles, but allows you to render 3D meshes and structures over them. This is just one demo. That's the UK plot with the hexagons over the UK. And lastly, I'll mention Plotly, which is one of the biggest and best known sort of JavaScript-based visualization packages. Also has a subset of its API that does 3D plots. Probably more on the traditional side, but it gives you controls to pivot around them and zoom them just like you can with most of the 2D Plotly plots. Cool, so I'm almost at the end. So for any further reading, watching, listening that you might be interested in, I mentioned that I'm a huge fan of Jake Vanderplas's materials and talks. So there was the talk that he gave 6 years ago now at PyCon US, the Python visualization landscape, which was the inspiration for my own talk. Despite it being 6 years old, it still holds up really, really well. Pretty much all the visualization packages he speaks to back then are still alive and well and heavily used these days. So that's really great. And another one of his talks that I particularly liked was how to think about data visualization. And this is less tech focused, but it's more about how do you compose good data visualizations and how do you use elements of visualizations in the most effective way to convey your message and to present the data as neatly as possible. So I think they're great. For a short kind of online ebook or reading, there's the Python in OpenGL for scientific visualization. I believe this is by the same author of that GlumpY package. Once again, it's a few years old, but it still covers a lot of these 3D concepts that I've spoken about and dives a bit deeper into them if you're interested in getting into the weeds a little bit more with them. Yeah, I've mentioned heaps of pretty cool looking 3D visualization packages, but as I said, as a starting point, I would probably recommend checking out that PyVista first if you're new to this domain, as I think that has one of the best kind of onboarding experiences for new developers, and because it just covers such a breadth of possible use cases for you. And I guess the last thing I mentioned that's not to do anything particularly with data visualization, but if you're interested in looking at shaders and what's possible with them, check out the Shader Toy website. So this site is a huge collection of these different shader functions, and they can do these amazing 3D renders that update dynamically in your browser, and it's a pretty cool ecosystem. So yeah, I'm pretty much at the end. So just to summarize, if you are thinking about doing 3D rendering and visualization, make sure the properties of 3D rendering suit the sort of message and data that you want to convey so that the features of it are working for you, not against you. And out of all that big selection of packages I've shown you, some things to think about when you go to choose one or other of them is think about whether they support doing pre-rendered visuals, if that's your aim, to like include them in a presentation or a talk, or whether you want to have interactive 3D visualizations, because that's a different set of libraries. Also think about your deployment story, whether you're deploying to a desktop application or whether it has to be browser-based. And lastly, think about the kind of scale and performance requirements. If you need to render a scene that's particularly realistic or just has very complicated 3D geometry, you might be inclined to look more at those packages that tie closer to the newer 3D platform APIs. And that's it. Thank you very much for listening. If there's time, I'm happy to take questions.
Thank you, Owen. Very good. We don't have time for questions, but we do have the Discord channel. You can pop some questions there, and then if you can log in and answer the questions. And obviously, you can hang around in the aisles and ask questions to Owen. Thank you. And here's a mug and thank you note for the conference. All right, so we'll be back in 10 minutes.